Welcome back to the part 2 of our chapter 5. In part 2 we're going to be going over random variables. Here, random variable is a numeric quantity that takes on different values depending on chance. There are two types of random variables. The first type is called a discrete random variable, which is a countable set of possible outcomes, the number of cases in a simple random sample from the population. The second type is called a continuous random variable, which is an unbroken continuum of possible outcomes, meaning that it's continuous, it keeps going, always going on. Discrete is an actual set of numbers in a possible outcome, i.e. our class experiment. There are a certain number of people in the classroom that we can count. There's not an ever-ending flow of people coming in or going out. It's not ever changing. And our class example is concrete. It's set. That's how I kind of remember. Discrete kind of sounds like concrete to me, and concrete set in stone. It's a countable set of outcomes. Whereas continuous is it's continual. It's always going. Discrete random variables, like I said. Concrete is a countable set. We want to think of these as probability mass functions, or you'll see it shown as a PMF, which is a mathematical relation that assigns probabilities to all possible outcomes for discrete random variables. So we're going to do an illustrated example of this using the 4 patients. So suppose I treat 4 patients with an intervention that is successful 75% of the time. Let X be the variable number of successes in the experiment. This is the PMF for the random variable. So here we have our 75% probability. So the probability of having 1 success, or I wouldn't put an S, success, or 0 successes, 1 successes, 2 successes, 3 successes, 4 successes. This is the probability of having those with a successful 75% of the time. So if we have 4 people that I treat, and how I treat them is successful 75% of the time, what is the probability that none of those 4 are actually going to be successful? And we'd say I'd have a 0.0039% chance of being successful. One of those 4 being successful is about 4.69% chance. 2 would be a 0.21 or 21% chance. 3 people being successful would be a 42.19% chance, right? And then for all 4 people being successful, there's a 31.64% chance of being successful. It kind of makes sense, right, that if 75% successful out of 4 patients, you'd expect at least 3 of them to be successful, right, at 75% in your head, which, if you look, 3 has the highest probability of being successful at 42.19% chance. So here is that exact situation again, just another illustrated example of it using the histogram here. So you have the number of successes, either 0, 1, 2, 3, 4. At the top, the probability of those success chances occurring, and here is your chart to look at. So this one just had more of a table. This is more of the actual illustrated example of the 4 patients in the histogram. With our probabilities, there's properties that we're going to be going over. There's 4 properties in all, and these are very important to understand. These are the 4 that you have to know. There are more that are talked about in the book and that we'll go over, but they get a little bit more advanced. But the first 4 are absolutely key, and you have to know. And the first property is the probabilities are always between 0 and 1. Probabilities are always between 0 and 1. You can't have a probability of 0 means it's not happening, and so a probability of something happening has to be between 0 and 1, 1 being 100%. Property 2. A sample space is all the possible outcomes. The probabilities in the sample space sum to exactly 1. If you were to take our patient example And our class example, how we're looking at them, all the probabilities added together are always going to sum to 1. So if we wanted to look at the males and females in our class example, if we were looking at comparing males and females, the probability is always going to sum to 1. If you add up everybody in there, the probability of selecting male or female is going to sum to 1. Property 3. The complement of an event is the event not happening. The probability of the complement is 1 minus the probability of an event. So anytime we have a complement, it's always going to be noted by the complement of A. So A with a line above it is the complement. If we had A would be the probability of an event happening. The complement of it, A with a line above it, would be called the complement of it, which is everything of the probability, the event not happening. Property 4. The probabilities of disjoint events can be added. We're going to go into an illustrated example for 4 coming up. So the properties of probabilities and the symbols associated with them. So when we say for the property 1, remember all the probabilities have to be between 0 and 1. The probability of event A happening has to be between 0 and 1. Property 2. The probability of the sample is equal to 1, where the S represents the sample space and all possible outcomes. Like I said, the sample space, everything in the sample space has to equal to 1. Property 3. Probability of the complement of A, here's our A with our little line above it, so the complement of A, the probability of complement of A is equal to 1 minus the probability of A. This is where we used to say the A line represents the complement of A, not A. So an example with our males and females in the classroom, if we had 20 people in the classroom there, and we had 5 males, right, and we wanted to find the how many people in the class were not males, that would be the complement of A. So the probability of A being males, the complement of males would be finding the females, or i.e. people who are not males. Property 4. If A and B are disjoint, then the probability of A or B equals the probability of A plus the probability of B. Disjoint here is meaning that they are separate, that you cannot be in one or the other. They're disjointed. So here are probabilities, or properties 1 and 2 illustrated. So we can go back to 5.2 and show that for property 1, the probability is always between 0 and 1 for the probability. Note that all individual probabilities are between 0 and 1. Property 2, the probability of the sample is equal to 1. Note that the sum of all the probabilities, if you were to add up the probabilities of the success of 0, 1, 2, 3, and 4 is equal to 1. Property 3 illustrated. Property 3 is the probability of the complement A is equal to 1 minus the probability of A. So here's your 4 patients, PMF. Here's our probability table. So as an example, let A represent 4 successes, shown here. So 4 successes, and here's your A, the event A, equaling 0.3164. Let the complement of A represent the complement of A, which is not A, which is 3 or fewer. So here's your A event, so we want to know everything that is not A, which is 1 minus the probability of A, which is equal to the sum of the rest of the group. Which goes back to the other properties where the total sum is going to equal 1. So if you want to know, if you know the probability of 4, the rest of the probabilities has to be 1 minus it, because the total sum of all the probabilities added up is always going to equal 1. Property 4 illustrated. So property 4 is the probability of A or B is equal to the probability of A plus B for disjoint events. So here's our 4 patients and PMF example again. So let A represent 4 successes, let B represent the 3 successes. So A probability of A event, and the probability of B event. Since A and B are disjoint, the probability of A or B is equal to the probability of A plus the probability of B, equaling A being 0.3164 plus the probability of B, which is 0.4219, which adding together is 0.7293. So the probability of A or B occurring, since they're disjoint events, you can add them together. The probabilities are in 3 or 4 successes is 0.3, or about 73%. So here we have area under the curve. The area under the curve, or the ACU, on a PMF corresponds to the probability. So in this figure, we have the probability of x equaling 2 is the area of the shaded region, which is the height times the base. So your height would be total probability going up, right? Total probability up 0.2109. The base is 1. So we'd say the area under the total number here is 0.2109. Cumulative probability. Cumulative probability refers to the probability of the value or less. Notation by the probability of x is less than or equal to x, corresponding to the ACU to the left of the point, the left tail. So here we have our example of the probability of x less than 2 equals the shaded tail region. So we want to know from 2 and less than the probability of that occurring. We know these are disjoint events, so you can add them together. So you add up the probability of 2 successes, 1 successes, 0 successes, notated here, and you're going to get your value of the probability of x less than 2 equaling 0.2617, or about 26%. Remember, I think the key point here to always know when we're doing probability and finding the area under the curve, for any probability, you're always going to the left when it's like less than. So make sure you know what direction you're going in. Continuous random variables. So all those examples were about discrete random variables. So now continuous random variables, continuous random variables form a continuum of possible outcomes. They're always occurring. They're continuing. As an illustration, consider a spinner on the next slide. The spinner will generate a continuum of random numbers between 0 and 1. So our other ones were more concrete. They're definitive. Where a spinner, you can always add just a little bit, right? Each one of those is a tick point and can continue to be. And then you can even go in between all those tick points and have a different value. And you can go even in between those tick points and have another value, and in between those tick points. And you can actually continuously always keep going in between them. So continuous random variables. A probability dense function called a PDF is a mathematical relation that assigns probabilities to all possible outcomes for a continuous random variable. The PDF for our random spinner is shown on the next slide. The shaded area under the curve represents the probability. For instance, so this one we want to know the probability between landing between 0 and 0.5. Which on the spinner, if we know, we go from 0 to 1, and the area under the curve is 5, right? There's 50% chance that you can land between 0 and 0.5 using the spinner. Oh, those are all supposed to show up later. So PDF obeys all the rules of the probabilities. Some PDFs come in many forms, shapes. Here are some examples. Here's a uniform PDF, a normal PDF, chi-squared PDF, and for exercise 5.13 is a triangle PDF. The most common PDF is the normal PDF that we've shown here. We study the normal PDF in detail in the next chapter. We will as you can see, this is a bell-shaped curve, and one that we will be going into a lot more detail coming up soon. So here are more rules of probabilities. I'm going to stop the slide here and go into those and start the next video. So I'll see you all.